In order to solve previously identified problems in current standard units, we need to trace back how those units were derived. The goal here is to have a unit system with uncompromising consistency according to all definitions and equations related to rotational quantities. Let's start with the most fundamental quantities. They are length, mass, and time, with units of meter, kilogram, and second, respectively. In relation to linear motion, the relevant quantities are displacement, inertia, and period. They have the same units as length, mass, and time, respectively. The base quantities are used to derive other quantities that describe linear motion. They are velocity, acceleration, linear momentum, force, work, kinetic energy, potential energy, stiffness, power. Velocity is derived as rate of change in displacement with respect to time. Its unit is meter per second. Acceleration is rate of change in velocity with respect to time. Its unit is meter per second squared. Momentum is inertia times velocity. Its unit is kilogram meter per second. Force is rate of change in momentum with respect to time. Its unit is kilogram meter per second squared, which is called Newton. Work is accumulation of force with respect to displacement. Its unit is Newton meter, which is also called joule. Joule is also the unit for energy. Kinetic energy is the energy of an object due to its motion. Its unit is joule. Potential energy is the energy of an object due to its position. Its unit is also joule. Stiffness determines the work involved in the process of displacement, as described by the formula of potential energy. Its unit is joule per meter squared. Power is the amount of energy transferred or converted per unit time. The unit of power is the watt, or joule per second. Converting linear motion into rotational motion can be done by applying a force perpendicular to the direction of motion. In a circular motion, this perpendicular or orthogonal force has a constant magnitude and is always directed to the axis or center of rotation, which makes it called centripetal force. Rotational motion can be described by quantities analogous to linear motion, as shown by this comparison table. Their names are similar to the linear counterparts, except some with unique names, like moment of inertia and torque, which are related to inertia and force, respectively. A rotational system can be described by both tangential and angular quantities, which are related to linear and rotational quantities as described previously. To avoid confusion and make it easier to compare, we'll just add angular to the quantity names instead of their unique names. One radian is the angle subtended at the center of a circle by an arc that is equal in length to the radius. Thus rotational radius equals tangential velocity divided by angular velocity. It's also equal to tangential displacement divided by angular displacement. To be consistent with the equation, rotational radius should have the unit of meter per radian. Let's derive angular quantities of a rotational system described by its tangential quantities. On the left side we have the symbols, derivations, and units of tangential quantities which are equal to quantities of linear motion. On the right-hand side we already have symbols and derivations of the corresponding angular quantities. Let's determine the anchor units first, which are the same for both types of quantities. These are period and energies, with units of second and joule, respectively. The next step is to derive angular displacement, which is derived by tangential displacement divided by rotational radius. Its unit is radian. Angular velocity and angular acceleration are first and second derivative of angular displacement with respect to period, respectively. Their units are radian per second and radian per second squared. We can also derive power, which is the first derivative of work per unit time. The unit is watt. Finally, we can derive the rest of the angular quantities. Let's start from the bottom, which is easier. Stiffness is twice of work divided by angular displacement squared. Its unit is joule per radian square. Angular force is first derivative of work with respect to angular displacement. Its unit is joule per radian. Angular momentum can be derived from integral of angular force with respect to period, with unit of joule second per radian. Angular inertia can be derived from kinetic energy equation. Now let's make the units previously derived more compact by changing them into joule-based units. This change makes the units of angular quantities more similar to their tangential counterparts. Converting a unit of tangential quantity into corresponding angular quantity can be done by simply replacing meter with radian. We can determine the conversion factor between tangential quantities and angular quantities of a rotational system. Previously, rotational radius has been defined as the ratio between tangential displacement and angular displacement, thus its unit is meter per radian. Using this definition, angular quantities can be converted into tangential quantities by a mathematical operation involving rotational radius. For example, angular displacement, velocity, and acceleration are the corresponding tangential quantities divided by rotational radius. Angular momentum and force are tangential momentum and force times rotational radius, respectively. Angular inertia and stiffness are tangential inertia and stiffness times rotational radius squared, respectively. Period, work, energy, and power have the same units in angular as well as tangential quantities. Let's compare the angular units we have derived with current SI units. For quantities where the angular and tangential units are the same, SI units are also the same. They are period, work, energy, and power. When the units of our derived angular quantities has radian as the numerator, like displacement, velocity, and acceleration, they are the same as SI units. When the radian appear as denominator, like momentum and force, it's discarded from SI units. This causes a problem because the SI unit for angular force equals unit for energy, which is Newton meter or joule. In angular inertia, radian square appear as denominator. It's just discarded in SI unit. Radian square also appears as denominator in angular stiffness. But in SI unit, the radian is not squared. This comparison shows how SI system treats radian inconsistently. It seems to appear and disappear arbitrarily. Perhaps it was influenced by practical and historical considerations. But viewing the whole unit system in a bigger picture can clearly show the flaws in our current standard. In the next video we will discuss the likely root cause of the problem, so stay tuned.